everyone. The first ITC lunch of the spring semester. It does look like spring, the sun is out. But it's still very cold, as Eugene can testify. We just had an excellent ITC colloquium, very pedagogical, was sort of like a class, I would say, that Eugene gave us. And should be translated to a textbook, hopefully, in the future. Actually, Eugene will speak a little later. We'll start with our own Jane Huang, who will talk about insights into planet formation from high-resolution ALMA imaging. And then we'll hear from the CFA colloquium speaker today, Daniela Calzetti. Should be here somewhere over there. She's coming from not very far away, UMass, and she will tell us about the scaling relations of galaxies in the infrared. And then we'll hear from Eugene again about the stellar winds and dust avalanches in debris disks. And finally from Carl Rodriguez, visiting us from the very distant MIT, about binary black hole mergers across cosmic time and space. Go ahead.
Hi everyone, it's San. I'm Jane Huang, a graduate student here at the CFA, and I'll be presenting today on the first high angular resolution ALMA survey of protoplanetary disks, which we call the Disk Substructures at High Angular Resolution Project, or DSHARP for short. And this is the collective effort of the people listed on this slide, which include a number of people who are currently or were recently at the CFA. And if you're interested in working on this data directly, all of our data and our reduction scripts are publicly available for anyone to use on the ALMA website. And our results were recently published in a series of 10 papers in AppJ Letters last month. We observe protoplanetary disks because we want to understand how the initial conditions of planet formation set the diverse range of exoplanet masses, compositions, and orbital configurations that we see in surveys. Over the last few years, ALMA has really been transformational in our understanding of protoplanetary disk structure. It turns out that the smooth disks of yesteryear are actually quite complicated. We see large-scale azimuthal asymmetries, concentric gaps and rings, and spiral arms. And from a planet formation standpoint, this has been really exciting because these features have long been predicted to be the outcomes of planet-disk interactions. But the story may not necessarily be that simple because a number of hypotheses have also been proposed to explain these same features. So in order to properly understand the origins of these substructures, we can't just look at a few serendipitous case studies. We need a proper survey to understand the morphological diversity and the prevalence of these structures, which motivated our current survey. We selected 20 nearby Class 2 protoplanetary disks and observed them at, in the 1.3 millimeter continuum. These are previous images of the protoplanetary disks, generally at a spatial resolution of about 30 AU. And although you can start to see some structures at this resolution, for the most part, the disks are smooth and featureless and look quite similar. But when you get down to a resolution of 5 AU, it actually turns out disks are highly diverse and highly structured. Two of these systems are in known multiple star systems, and in each case, we can see that the primary disk has a two-armed spiral feature. And this is the predicted outcome of dynamical interactions between a disk and an external companion. On the other hand, we also have found 3 disk systems with spiral arms that don't have known companions. In the bottom row, we replot the continuum intensity as a function of polar angle and radius. These annular gaps you see manifest as these vertical bands in these polar plots, but the spiral arms are diagonal bands of emission. The spiral pattern can be seen more readily once we subtract an axisymmetric intensity profile. And again, the annular substructures are marked with these white lines. And in the Elias 27 disk, we can actually see that the spiral arms cross the gaps, which is rather curious. The leading hypotheses for how we form these spiral structures in protoplanetary disks are either through gravitational instability or planetary perturbations. Previous analyses of disk masses suggest that the disks are not massive enough to trigger gravitational instability, but disk masses are also notoriously difficult to constrain. For the other possibility, planetary perturbations, simulations suggest that in order to generate these very open m=2 spiral patterns, we would need a quite massive planet, perhaps on the orbit of several Jupiter masses. So in principle, a planet this large could be imaged directly. To that end, one of the co-PIs of our ALMA survey, Laura Perez, has an ongoing VLT program to search for possible planetary companions. By far, though, the most common type of substructure we see are these series of concentric gaps and rings. So knowing this, we can say that ring formation is not a specialized process. We see these structures occurring basically everywhere in the disk, as close in as a few AU, which is basically almost resolution limit, and as far out as 150 or 200 AU. We see them in disks orbiting stars across a range of spectral types from M through A. Most of our targets are about 1 million years old, which tells us that ring formation can occur very quickly. But we also see these ring structures in disks up to 10 million years old, which would suggest either that the disk structures are very long-lived or that they can form very late in the disk lifetime. One important caveat is that ALMA has disproportionately targeted disks on the larger end of the population. So in order to properly understand the entire disk population, we will eventually need to observe the smaller end of the disk population. The oldest and longest standing hypothesis for how we form these structures in disks are that the gaps are opened through the torque exerted by a massive protoplanet inside the disk. And this mechanism is illustrated here in this simulation by Jae-Han Bae. We start with a smooth protoplanetary disk surface density profile, and then as a planet grows, it'll trigger a spiral density wave, which will eventually shock and open up a disk gap. A variation of this idea that's been explored more recently is that in a sufficiently low viscosity disk, a single planet might actually open up multiple gaps. As an example, one of our team members, Shanja Zhang, ran a hydrodynamical simulation with a 0.1 Jupiter mass planet orbiting at 99 AU, which is this big gap here. And you can reproduce most of the substructures that we see in the AS209 disk. More generally, the radio intensity profiles of our disks show a wide range in width, depth, and locations. And in the framework of planet-disk interactions, the gap width and depth scale with the planet-to-star mass ratio. So taking this information, Shanja Zhang ran a grid of hydrodynamical simulations to compare the gaps in the models to the gap widths that we measure in the D-sharp observations. And he plotted the inferred planet masses and semi-major axis with the known exoplanet population. The planet masses he inferred here are plotted in orange. And as you can see, these inferred planets occupy a part of parameter space that isn't really well covered by current exoplanet detection methods. The orbits are generally at a few tens of AU, and their masses are somewhere in the range of the ice and gas giants in our solar system. And this is generally consistent with findings from other papers that have analyzed individual disk gaps. A different idea that doesn't invoke planet-disk interactions is that the complex substructures are a consequence of the coupling between the disk magnetic field and the disk material. So for example, MHD simulations indicate that at the boundaries of dead zones where ionization is suppressed in disks, we should see axisymmetric surface density variations, much like what we see with ALMA. But these same simulations also suggest that a lot of the time, these processes will create vortices, which will lead to strong asymmetries in intensity. And although in a few cases we do see such strong azimuthal asymmetries, for the most part, we don't see these structures in our survey. So that suggests that these MHD processes don't explain the majority of the structures. A different idea is that the gap in ring structures trace molecular snow lines. And the general idea behind this mechanism is that the sequential freeze-out of volatiles in the disk will modify the coagulation and fragmentation properties of the dust grains, which will lead to pileups at characteristic radii. And in this scenario, then, we would expect the substructure locations to track with the temperature. So given the stellar luminosity, we can create a rough estimate of the disk temperature. And so we've plotted the radial intensity profiles as a function of the midplane temperature rather than the radius. And we've also shaded in the regions where we expect major volatile snow lines in the disk to occur. We don't plot the water snow line because in general we expect it to occur too close to the star to be resolvable by ALMA. But in general, we don't seem to see any trends with temperature, which suggests that snow lines don't directly set the majority of the substructure locations that we see. And this is in accordance with conclusions that were reached in a couple other recent papers that analyzed different disk samples. So in summary, complex dust structures in protoplanetary disks are common and maybe even ubiquitous. And we argue that the planet-disk interaction interpretation is the most plausible explanation for the structures that we see. If these structures are indeed due to planets, then there are at least two interesting implications. The first is that planet formation is often well underway within 1 million years, which is fairly fast. And the second is that giant planets can form readily at large orbits. Thanks for listening. Does anyone have questions?
Jane, these are beautiful results. Is there any prospect for imaging that? So, I mean, it does sound like you make a very good case that these might be produced by giant protoplanets. Is there a way of imaging them, either with JWST or ALMA? Can we see the emissions from those?
So with ALMA, we wouldn't see the planet directly, but people are searching for the circumplanetary disks around the planet. And so for direct imaging, there are prospects for imaging the upper end of the mass range around Jupiter or so, but it's not clear that we'd be able to probe the putative population of, say, Neptune-mass planets.
Because if this is confirmed, it would be a new way of finding this population of planets that were not found before, right? That's what you're saying.
That's sort of the implication, yes. But the other comment I should make is that it's possible that the planets migrate, so it could be that they are related to the currently known exoplanet population, just we're seeing them in much earlier stages of evolution.
Yes, go ahead.
It's beautiful data. In the background image, top row middle, there's a very bright asymmetry that is south and west. Is that one of those dust traps like in HL Tau?
Which side? Okay, which one?
Top row middle.
This one?
Yeah.
So we interpret that as a dust trap, which is an area in the disk where due to the gas pressure, large dust particles are trapped and highly concentrated. Yeah.
Then, just a curiosity, when you showed the binary, and you had two disks, they seem to be misaligned. Is
They
there
are.
a reason for that?
Unclear why.
Eugene?
So depending on the viscosity and how much time has elapsed, the planet can either be situated in the center of its gap, or it can be in the overbright ring. It can open two gaps to either side. So in your interpretations, do you find mostly that you get good fits when the planet is inside a density minimum or a maximum?
That's a good question. So actually, I think we see both scenarios trying to get to the radial profiles. One particular interesting disk is AS209, where you actually, it's hard to see here, but there's actually a slight bump in that giant gap. And so our interpretation is actually this is one of the low viscosity disks where you have the planet inside the ring, and then you have double gaps on either side. But in other disks where we don't see multiple gap features, then we just interpret that as a high viscosity disk with the gap opened by a single planet.
Charlie, you had a question?
Yeah, in that, if you go back to your postage stamp series from ALMA, and again, I got a question with that same disk, HD 143006. In the very center, it looks like there are two bright spots that are opposite each other. Do you know what that is, or you have any?
So two comments on that. One is that if a ring is not well resolved, it will naturally have the two bright spots. But the other is that there are indications that this disk is warped from scattered light observations, so that also contributes to it looking not as round as the other rings.
Over there. Yes.
Can you go back to the plot where you have the scattered plot of the planetary properties that you infer? I think I want to better understand the implications. Are you for example, surprised by the fact that with this sample size, you see no plants that really overlap with the highest density region of other methods? Or is that just an observational bias?
So our resolution is about 5 AU, so we're not going to see anything. We're not going to see anything in this resolution.
Okay.
I was just curious as to on what your estimates of age were based. You said this million years old. That's 10 million years old. What gives you the handle on the ages?
So they're based on evolutionary tracks of Isabella, right? Yes. Oh, Gene Choi's missed models.
Any other questions? If not, let's thank Jane.
Okay. So thank you very much for inviting me, and this is going to be brief, despite what I threatened last night, and it's going to be more of a question than something with a concrete conclusion. So I will appreciate any question you might have. Fundamental parameters for galaxies. So we move away from planet-forming disks. We move into external galaxies, just to reframe what we are looking here. And what we are dealing now are the fundamental characteristics that you would like to measure in galaxies. Star formation rates, masses, and thanks to ALMA and other millimeter and radio facilities, the dust content of galaxies. These are fundamental parameters that allows you to follow the evolution of galaxies as populations across the universe. I'm actually showing here a rendition of the cosmic star formation rate density as a function of redshift. This is a plot that I lifted out of a recent paper by Caitlin Casey. It shows the star formation rate density per comoving volume in two bands. The observed UV, which are the blue points, and the observed infrared. If you're measuring star formation rates in the local universe, you will never discount dust. And if you do, well, that's your problem. Of course, that doesn't mean that it's a problem also at high redshift, but observation seems to indicate that at least up to redshift 2 or 3, and possibly a higher redshift, we do have to worry about dust and dust corrections of star formation rates in the universe. But you can turn the argument around and say, well, we can use dust emission to measure both star formation rates and dust masses that we can, with educated guesses on the dust to gas ratio, convert to gas masses. So we have one SED, the infrared, and we can make two measurements. Use the blue side to measure, let's see if I can get this to work. Oh, sorry. Okay, so we can take a spectral energy distribution in the infrared just to orient you. This goes from about 2 microns all the way to 1.1 to almost 2 millimeters. This is a Spitzer 8 micron, Spitzer 24 micron. Herschel, Pax, this is a 70 micron, 160 micron, and this is a data point in the millimeter band. This is from ALMA. This is 1.2 millimeters. Okay, and the black line is a fit to the energy, spectral energy distribution in nu as a function of log lambda, or lambda as a function of lambda, of using the Drenelin models, okay? And what you see here highlighted in color are the cyan band, and the magenta band shows you where you will measure star formation rates. Okay, they've been calibrated. And the reddish band to the right of the peak shows you where you will measure the gas mass, the dust mass, and then convert it to a gas mass. So star formation rate to the blue side, gas mass to the red side. Now, we are not new to using the same spectral energy distribution to measure different quantities. You use the UV, if you can handle the dust, to measure star formation rate. You use, say, the red bands, long word, say, or the I band, to measure total stellar mass, okay? But, in that case, you know that your stars are mostly contributed to the UV if they're short-lived and massive, and the red bands are contributed by all stars, including the low-mass ones that contribute most of the mass. In the case of the infrared SEDs, things are not so clear-cut, because it's true that as you go to longer wavelengths, you are dealing with cooler and cooler dust. But the problem is that the short wavelengths, the ones that you use to measure star formation rates, also can be heated by low-mass stars through single-photon heating, the infamous stochastic heating of dust. Okay? That allows low-mass stars to heat dust in these bands as well as in the bands that trace the dust mass. So what you have to worry is how much covariance do we have between the blue side and the red side? And can we use them? Why? Why are we asking this question? Because once JWST is on orbit, you're going to have a fantastic machine, actually a combination of two machines, JWST and ALMA, one probing up to redshift 2, not only galaxies, the galaxies themselves in the 8 and 24 micron, mostly 8 micron if you're at redshift 2, but regions within galaxies. You're going to be able to slice and dice galaxies in regions within a redshift 2. Regions within galaxies at redshift 2. Something that has not been, has only marginally been done so far. And ALMA, we provide a complementarity at the longer wavelength to measure the dust mass, the gas mass. Good. So how do we go about that? Well, one regime where we have all the data we can possibly dream of, or almost all of them, is the nearby universe. And when you're dealing with galaxies in the nearby universe, you don't want really to compare a galaxy at redshift 0 with a galaxy at redshift 2, which is tendentially less evolved, especially if your plan is to look at regions within these galaxies at redshift 2. So what you're going to do then is to slice and dice your nearby galaxies and try to concentrate on sub-kiloparsec regions, say a few tens to a few hundred parsecs, to try to isolate and separate regions of intense star formation from regions of low star formation. So these are two examples here. This is a galaxy that we observed with the LMT at 1.1 millimeter, and this is the region that was targeted, and this is a three-color composite in UV 24 and 70. As I said, we have every single possible measurement we can think of for these galaxies. This is M83, so a nearby starburst, and ALMA targeted the central region, and this is the equivalent of Spitzer 8 micron. It looks ugly, but on the screen it looks better. So you can combine regions with 4 regions within galaxies that are less than about half a kiloparsec. Spitzer, similar resolutions from Spitzer, Herschel, and LMT on ALMA. LMT is about 8.5 arcseconds. ALMA usually is much higher angular resolution. What do you get when you combine different bands? So this is, just to help you orient, this is the 8 to 24 micron ratio, okay? The blue band. The vertical axis is the 70 micron, which usually is close to the peak, to the 1.1 millimeter emission. Red band, peak to red. You see a nice, beautiful correlation here. Okay, depending on which camp you are, you may despair or rejoice, as seen in such a correlation, right? Because it could tell you, oh, I have an easy way of inferring, given 3 quantities, I can infer the 4th, assuming, say, for instance, I can see the 8 and 24 and the 1.1, I could infer the peak of the emission in the infrared. But you could also despair if you interpret this covariance, you try to understand the physics underlying this covariance. And in particular, you could have a trivial correlation because both the 8 micron and the 1.1 millimeter are tracing cold stars, low mass cold stars. And the 24 and 70 micron are tracing the hot stars emission, heating, sorry. Okay? Then it means that your 8 micron cannot be used as a star formation rate indicator. And that's a problem, because JWST at redshift 2 at 24 micron will be probing the 8 micron rest frame. Could be physical, because there is a mechanical law. And so if you have more star formation rate, you have more dust, or vice versa, sorry, more gas, or vice versa. And so the correlation could be physical. The problem is that we don't know yet. What we know is that if you go and zoom in into individual regions of the galaxies and try to understand where we're looking at, okay, so this is the same plot as before, but now I'm isolating 2 points here. Okay, one region on the top left, okay, to understand where something that is high at 70 micron and low at 8 micron might be. And that's actually a strongly star forming region. It's actually this noble star formation here. And if I map it back at this point here, that's the empty spot here. And indeed, it has a very cold SED, while the other one is very hot and typical of a star forming region. Where do galaxies stand on this same plot? Well, you can imagine that nearby galaxies, being complex systems that mix different populations, will actually tend to occupy the area where you find less star formation, less strongly star forming objects. Why? Because by covering factor, regions that are not star forming are far more frequent than regions that are star forming. And therefore, their line ratios will dominate over the ones that are strongly star forming. So again, strong star formation, top left, low star formation, bottom right. And so galaxies, whole galaxies tend to be mostly in this regime. Am I at the bottom, at the end of my 10 minutes? Okay, I have one more slide. So whole galaxies don't help, so you have really to zoom in. Where do models stand? Because the other question is, okay, where are the models? Right? What are the models describing? The models are all over the place. The models do not trace the same trends as the regions that you observe in the real universe. They actually can allow a much wider coverage parameter space coverage than what you have observationally. So this is my last slide, because I don't have an answer. Conclusion? Not yet. We still need to investigate and understand. And especially, how do we make the models to reproduce what we observe? Assuming that what we observed is correct, okay? Because I haven't told you whether it's correct or not. Okay, that's all.
Fraction of dust producing galaxies which is residing in the intergalactic medium carried out by these outflows?
So we definitely see dust being carried out. It's enough to look at the Spitzer image of M82, right? M82 is a nice edge-on galaxy. It has a starburst in the center. You image it 8 micron. You find 8 micron emission up to over a kiloparsec, I think several kiloparsecs away from, at least a few kiloparsecs away from the center. So definitely it's carried out. My understanding is that it might not even survive. So, because you have the possibility of sputtering and destroying the dust in the harsh environment. So, it's unclear to me. There are metals for sure, they are carried out. Even the dust itself would be a way to carry out metals. But whether that survives or not in the long range, I actually honestly don't know. My understanding, and it's not my field of expertise, is that it doesn't survive for long. Yes. Yes, I believe there have been analyses that seem to imply that there isn't much effect from the dust attenuation itself. I remember at least one paper. Could have been more than one.
Have you looked at the gas mass estimates that you would derive by observing CO?
This has been done. So, in terms of total masses, I don't know if this has been done. In terms of distribution of mass, what you typically see is that whenever you look at CO, you're looking at a much more concentrated version of the H2 than when you try, say, to look at the dust after subtracting the H1. So the dust distribution, the dust mass, you subtract the H1. First you convert it to a gas total, to a gas to dust ratio. Then you subtract the H1. What is left is usually far more extended than what you would get from a CO.
I'm curious about different kind of models. So if you take models of whole galaxies and then you make synthetic observations of them in these bands, what does that say in terms of whether it's physical or
So the models say that the 8 microns should not trace star formation. But you also have a luminosity effect. So models don't take into account the fact that you are luminosity weighted when you're looking at a galaxy. So it really depends on how prominent your star formation is relative to your non-star forming regions.
But I'm saying you take a model of a galaxy that has that whole mixture and then you make synthetic observations using models of the telescopes that you're using to make these observations, and you just made this plot. What does that look like?
It would distribute like with these models here. These are the models, right? If you don't know anything a priori, so you don't try to constrain the observations, these are what the models predict. This is an allowed parameter range of potential models of galaxies. So these colored data points, the color points. So the light gray, the magenta, the cyan, and the blue. That is the permissible parameter space coverage of models that reproduce galaxies. Well, that can potentially reproduce galaxies or dust that can physically exist.
By the way, Daniela, it's always said that the only people that believe models are the observers, and the only people that believe observations are the theorists.
That's why I'm here. That's why I use models, because I'm an observer.
I just wanted to know that maybe this also can, so when looking at high redshift galaxies, you would expect that the metallicity would be lower typically, and also the dust-to-dust ratio may be even extremely low. So instead of assuming a dust-to-dust ratio, maybe this could be used to infer the dust-to-dust ratio in these galaxies and how it scales with metallicity.
If and only if this is correct. Charlie, you had a question?
Yeah, in the case where you've got regions within galaxies, how much do you have to worry about non-local heating? So starlight from outside the aperture. In the case where these regions are semi-transparent.
Right. So I haven't done the analysis directly, but Lawton 2010, they did an analysis because they were looking at the Magellanic Clouds and they were trying to infer spectral energy distributions of regions within the clouds, and they analyzed a little bit exactly that effect. And I can't remember how they did the analysis exactly, but their conclusion was that it was relatively small, relatively minimal. You have to make sure that you're not looking at a diffuse region which is neighboring a very strong region, right? So you still have to be a little bit above the so-called galaxy background. So that is the only concern you have to worry about. In this case, definitely at the top right, at the top left, you wouldn't worry. Maybe it's a little bit of a worry here, but then, if anything, this would make it worse than what it is.
Okay, we need to move on. Let's thank Daniela. Thank you. Okay, can people hear me? They're good? Okay, thanks very much for the opportunity to give a second talk. This time on debris disks. So by definition, disks composed of optically thin dust, produced from the grinding of larger parent bodies. These are systems that are 10 to the 7, 10 to the 8 years old, thought to trace the aftermath of planet formation. In many cases, the parent bodies, the things that are producing the dust, are confined to rings, so analogous to the asteroid and Kuiper belts. Sometimes that ring geometry can be hard to make out when the system is observed edge-on, but with careful analysis of surface brightness profiles, you can back out that indeed the parent bodies really are concentrated into a ring. It was a happy day when Dave Wilner called me up and said, yeah, we found it in the thermal millimeter, no worries about forward scattering. You see this beautiful limb-brightened ring having a mean radius of 35 AU, fractional width of a few AU, which we called the birth or the primary ring. It was a real surprise. So dimensions comparable to the Kuiper belt, right? Except orders of magnitude dustier. It was really irritating. We thought we figured everything out. It was super surprising to have the case reopened by Bacaletti et al., discovering surprising time variability in the debris disk. This is with sphere on the VLT. All the action, it's very puzzling. All the action is happening on one side of the disk. You can already see something weird is going on, even in this original HST image, these ripples. These overdensities on the southeast ANSA, okay, and they have proper motions, they're moving. And the further away they are from the star, the faster they're moving. The most distant clumps are moving greater than the local escape velocity. So who ordered that? I'm a sucker for problems like these, where there's no explanation, not even at the to 0th order, because it gives me excuse to practice my order of magnitude estimation skills, which is a creative exercise, but also very cheap. So I like doing it. What orders of magnitude are we trying to explain? We're trying to explain why it is that these clumps have characteristic sizes of a few AU. We're trying to explain why it is that the characteristic masses are about this. The masses, this is observationally inferred from the observed surface brightnesses of these clumps. And I won't translate for you, right? I won't go through the exercise of translating the surface brightness into a mass, because I don't want to remind you of the trauma that many of us felt in trying to convert a unit like magnitudes per square arc second into anything resembling reality. It took me a day. Okay, so characteristic masses, the clumps seem to be emitted every 10 years or so. Okay, so what is going on? Well, this is what we think is going on. AU MIC, an M dwarf, young, active. M dwarf emits a wind. The whole show, we think, is driven by the stellar wind. Okay? We know that the AU MIC is emitting a strong wind. We know because it flares in X-rays and in UV. Mass loss rates inferred that are at least hundreds of times larger than the solar mass loss rate. The big assumption that we make is that this wind has a cycle to it, about with a 10-year period. Okay? That's an assumption that we make. When the wind gusts, which it does about a quarter of the time, it exerts a ram pressure force on submicron-sized dust grains that exceeds the force of gravity by a factor of 20. Okay, so this is the wind that's repelling these grains outwards. Here's a bird's eye view of everything. Here's the primary ring. Now you have to imagine, but I'll explain in a second, that all of the dust, the submicron-sized dust, is produced at one location, a very special location, almost along the line of sight to the star, and that it doesn't move. It does not move. It stays fixed in inertial space, even though the ring is rotating underneath it. So I'll explain in a second why that is. It took us forever, but there it is. There's a source region, okay, and it's easiest to see in an animation. And this is work done in collaboration with Sagan Fellow at Berkeley, Jeffrey Huang, who made this nice animation, which I'm going to show you. So when the wind, so the dust traces out this zigzag pattern, and it's all thrown over to the southeast, right? Just because it inherits the disk rotation. So that's why you see everything to the southeast, because it's rotating from the northwest to the southeast. Okay, but it's a zigzag pattern, right? So every time the wind gusts, you get a radial zig, and every time the wind is in the low state, you get a horizontal zag. And the overdensities, these overdensities that you see in projection, the observer is looking this way, correspond to the radial zigs, because that gives rise to the larger line of sight column densities. That's all it is. Okay, here's how we do for the projected velocities, trying to fit the observed clump velocities. What can I say? It's order of magnitude. Got the sign right. I think we can do better. There are a couple ways of doing better. One is we can move the birth ring a little closer, maybe 25 AU, and Dave Wilner tells me that there is material inside of the main ring in 35. We can appeal to that. We can speed up the velocities a little bit. Maybe we can also appeal to a little bit of magnetic pickup as well, just a little bit to bring up these latter velocities. So why is it that the source region remains fixed? This took forever. We tried all sorts of things, but I think the explanation, at least to me, is obvious in retrospect. So that source region is where it's very special. It's because it's where the primary is intersected by another ring. A secondary ring, much less massive than the primary. The secondary ring is just the remains from some single body that was disrupted in the past, right? Catastrophically broken up into bits and pieces when it collided with some projectile in the primary. Okay, and that's why, so these two rings, today, they're continuously grinding against each other and producing the submicron sized dust, which is then blown out like an exhaust valve through that region. Okay, and that intersection region won't move, aside from some slow precession. The scales are right. So, the characteristic cloud sizes, what's the size of this intersection region? Scales with the thickness of the secondary ring, which scales as the velocity dispersion, right, of the originating collision. And I'm going to use an ejective velocity on the order of a few hundred meters per second, which is just right. It explains things like the Haumea collisional family, which is known in the Kuiper belt. So that gives rise to a 3 AU size. So that works out. A few hundred meters per second tells you that the body that was disrupted could not have been larger than a few 100 kilometers. Otherwise, the surface escape velocity, 300 meters per second, is not enough to disperse the fragments. So just to give you a sense, 400 kilometers is about the size of Varuna, which in the pantheon of Kuiper belt objects is among the larger ones. And it's an interesting feature of the Kuiper belt that the larger objects are all in what planetary scientists call the scattered disk, and what I like to call as an astronomer, the thick disk of the Kuiper belt. And it's very interesting. The thick disk of the Kuiper belt is composed predominantly of these larger objects. So what we're imagining here is that AU mix thick disk, one member of it was blown apart to pieces, giving rise to this phenomena today. It's at traffic intersections, of course, where collisions are most violent, and we need these kilometer per second on the order of the orbital velocity in order to produce these submicron-sized grains. Because you're trying to disrupt micron-sized grains into submicron-sized grains, and the strengths of these small, nearly flawless targets is pretty large. If you know anything about material strengths, you do need on the order of a kilometer per second to break it up. It doesn't last very long, something like 30,000 years we estimate for the whole thing to go away, which either means we're super, super lucky or this has happened in the past. And all we're looking at is the latest casualty in a string of disruptions numbering in the hundreds. And by the way, on the order of 1,000 Varunas is about the population of the thick disk today in our Kuiper belt. So these numbers that we're getting are very Kuiper belt-like, so it's interesting. Okay, can we explain the cloud masses? We can with Jeffrey's idea of dust avalanches. So what is, an avalanche, just like any other avalanche, right? Electron avalanche in PMT tubes, photon avalanche, otherwise known as a laser, snow avalanche, which is what happens when I go skiing. It feels like that anyway. So you take these grains and they're being accelerated by the wind to kilometer per second velocities, and they create more grains. And I thought at first that these dust avalanches, this exponential chain reaction, would be impossible in an optically thin system like AUMIC, but I'd forgotten that it's not just one making two making four, it's one making 400, okay? And so even in an optically thin system, you can get an exponentiation along the path, which is very good for explaining the cloud mass. So since my time is out, maybe I'll skip the magnetic field and just say that we worked on this for a couple months. I'm basically summarizing my summer 2 years ago. This was work done with Jeffrey, and it happened in August, which is when the Perseids happen, right? The Perseids always happen in August, right? It's because, right, that's where the Earth's orbit intersects the meteor stream. So it's just like that. And I used to invite all my friends to say, hey, there's going to be the Perseids. But I don't invite them anymore because what they're expecting to see for a meteor shower is this. Okay? And then when we get out there, we see like one, and then wait 10 minutes, and maybe we'll see another one. And so I've stopped asking my friends to do this anymore. However, if you lived in AUMIC, this is what you would see, okay? I think it really is what you would see. So I just want to leave you with that. Okay, thanks.
Beautiful work. I assume that you checked that you need to grind it down to 0.1 micron because then the surface to mass ratio is such that...
Yeah, exactly. Yeah.
But then, is it true that the radiation itself from the star is not able to sweep these things?
It's an M star, so that's the first thing we checked. And so it's not strong enough. It's an M star, yeah. And the optical constants are such that you don't even get a full geometric cross section. Yeah.
Eugene, you invoked this fact that there's this varuna that comes from a thick disk equivalent. Well, how does that compare with the vertical thickness of a disk in the millimeter wavelength?
Oh, so it's
Do you see a thick disk?
No, you do not. So there's no direct evidence for the thick disk. The primary, the millimeter wave image that you're referring to has an opening angle of something like I forget, but h over r is something like 5% or something like that. So you do not you see the thin disk, the primary, but the thick disk, it's all, I think, it's all in these big objects that have just so little surface, so little emission surface area, right?
Wouldn't they collisionally grind as well to produce an observable?
They do. They do. I haven't worked out the cascade yet in the thick disk, yeah.
So I hate to be this guy, but what about magnetic fields?
Oh, magnetic fields help you. Well, I think. So you'll notice, right, that these ripples, I mean, it's really bizarre. These wavy patterns. So there's a Lorentz force, and the submicron sized grains, UV field of the M dwarf, charged. Okay, so we'll charge the grains, just photoelectric emission. It'll just charge the grains. Interact with the magnetic field of the wind. The wind has to be magnetized, right? It is a low mass star. There's no way out. So it's the V cross V force. V is the VR from the wind. The B is the phi, because it's wrapped up by the time you get out there. R cross phi is Z. That's good, because you see these up and down motions. Okay, so and the field flips every 10 years, maybe. Right? Okay, to keep the amplitude finite. And so I can, I can keep the amplitude of the oscillations limited to about a few AU. The reason why I laugh is because, if you look in detail, this clump here looks like, I was encouraged. It's going down. That's good. I want to go up and down, up and down. It's just simple up and down. But this one, look at B. I mean, I don't know what's going on. It just kind of hovers out up there. So I don't know what's going on there.
I might have missed it, but is there something special about the system that creates this, or do you expect this to be common?
So it's an M dwarf, and M dwarfs have strong winds. Most of the other debris disks, many of the other debris disks are seen around A stars, so we don't expect this sort of activity. It's edge on, so you get extra beaming from that, right? Yeah, I mean, if this were to happen on the other side of AU-MIC, then I think it would be much harder to see because you wouldn't get the forward scattering. So the fact that it's an M dwarf, and the fact that you're looking at it edge on, and the fact that it's almost along the line of sight, gives you these special circumstances. So I would have said the short answer is it's a special circumstance. Well.
If there is this sort of period of increased activity around every 10 years, do you have any expectation when we might be able to see that, or should we just observe it for 10 years and see if something happens?
Well, people are continuing to observe it. I will admit that the latest paper by Calzetti they didn't see this before, but with better data reduction, they actually see a clump, maybe even two, just to a little bit to the right of the star, so over here. So there are new things appearing. They're all moving to the southeast. Yeah.
Thank you much. Oops. There we go. That's slightly better. All right, can everybody hear me? All right, so I'm just going to talk briefly about some of the work that I've been doing, a little bit actually with people here at the CFA. Oh, my name is Carl Rodriguez, by the way. It says it up there, but I figured I'd say it anyway. I'm a Popularta fellow right up the road, but I come over here occasionally because y'all have nice sandwiches and good theorists to talk to. And I'm going to talk briefly about just a couple of projects I've been working on. I'm just going to sandwich two of the results into maybe a few slides. And some of the projects I've been working on actually involve some of the people here, so actually involve Avi and some work similar to what Dan Durazio has been doing. But I always like starting off my talks with this picture just because it really hammers home exactly how much the field of stellar mass black holes have changed over the last 2 years. So for the first 50 years of black hole physics, everything we knew came from X-ray binaries, right? And that's all the way from SIG X1 all the way up until circa 2015. And in that last 2 years, LIGO has detected around 30 stellar mass black holes, depending on how you count, which is kind of an insane thing to realize, right? In 2 years, we have detected the majority of the black holes we've seen through gravitational waves at this point, which is just a mind-boggling statistic. Believe it or not, though, we still don't entirely know how you get two black holes close enough together to where they'll merge within the age of the universe. But the two basic formation channels generally follow one of two pathways. The first is that you start off with a massive stellar binary. You have stars about 40 to 100 times the mass of the sun, and you turn your normal crank on binary stellar evolution. So the first star goes supernova, or just directly collapses into a black hole. The second star evolves onto the giant branch, eventually overflows its Roche lobe, swallows the primary black hole in what we call a common envelope phase, which Morgan is one of the leading experts on, and then through some complicated gastrophysics that we don't fully understand, the orbit shrinks due to losses through dynamical friction and injects enough energy to unbind the envelope. At that point, your secondary collapses to a compact object, and you're left behind with a compact binary black hole system. This is what we typically call common envelope formation of binaries. The other way to do this is you dispense with the pre-existing binary entirely, and you start off with two unbound massive stars. In this case, you don't have to solve the complicated gastrophysics of the separation problem, and your stars just evolve along their merry way. Now here, you have to solve the problem of getting these things into a binary that'll merge. Of course, if I just toss two compact objects or any two Newtonian objects at one another, you can't form a bound system, right? Positive energy in, positive energy out. But if I happen to have a nearby companion or some sort of third body involved in this encounter, I can dump some of that excess energy and angular momentum onto it, taking this unbound encounter, or rather this positive energy encounter, to something that produces a net negative energy system. In this case, I've formed a bound binary and dumped some of the excess energy onto this nearby companion. This obviously doesn't happen in galactic fields a lot because the stellar densities are way too low, but there are regions of space, like say dense star clusters, where this sort of dynamical formation actually operates, we think, fairly regularly. Now, the name of the game at this point is not to come up with more theories to create binary black holes. We have, at this point, still more theories than we actually do observations, because, theorists need to earn a paycheck. The question now is, can any of these theories actually produce the current merger rate as inferred by LIGO and Virgo? Just to refresh everybody's memory, in the local universe, depending on your underlying mass distribution or what you've assumed about it, the merger rate is anywhere from on order a few to about 100 binary black hole mergers per gigaparsec cube per year. So around about May of this year, give or take, I was talking actually with Avi, and we noticed that there are now a large number of models based on cosmological simulations and halo merger trees and gas physics that actually create a sort of cosmological way of looking at star cluster formation across cosmic time. So not just taking measurements of the star formation rate or taking your favorite star formation history from a cosmological simulation, but actually coming up with nice cosmologically motivated ways of tracking star cluster formation across cosmic space and time. This particular one is taken from Kareem El-Badri, who's a grad student at Berkeley, and he basically just took a bunch of understanding about various gas flow physics, star cluster formation, and the sort of assembly history of galaxies, and actually came up with a nice model for producing globule cluster populations that seem to reproduce what we see in the local universe. So our idea was, well, we have these nice sort of semi-analytic approaches to cluster formation. I myself am a bit of an expert in doing dynamical simulations of star clusters and extracting the binary black hole properties out of this. Should be really easy to just convolve these two and actually come up with a nice rate estimate. And then we could just compare that and see whether or not this reproduces what you see from LIGO Virgo. And the answer, in very short, is yes. So it turns out, if you do this, you get this nice sort of smooth distribution that increases as a function of redshift. So going all the way out from redshift 10 up into the local universe, you get this nice co-moving merger rate that evolves based on the formation and evolution of globular clusters throughout cosmic space and time. And the peak is actually determined by the delay between the formation of these star clusters and the mergers of their black holes many gigayears later. And so the merger rate predicted by this in the local universe is about 10 to 15 per gigaparsec cube per year. Compare that to the LIGO Virgo merger rate, and you actually see that we can easily explain the majority of these objects that LIGO is seeing. And so we decided to take this one step further and ask the question, what happens if I compare this to different populations and ways of forming binary black holes people have proposed. So this is the co-moving merger rate from globular clusters, taken from the paper with Avi. You can also compare this to the distribution you might expect for triple black holes, where the Kozai mechanism actually drives black holes to merger. And you can compare this to the isolated binary evolution, the common envelope evolution in galactic fields. And for each one of these, you get overlapping but distinct peaks in the binary black hole merger rate at different redshifts, which of course makes sense. You have radically different physical ways of creating binary black hole mergers, and so of course they're going to couple to the star formation history of the universe in distinct ways. And you can of course combine all of this and play the game, what fraction of these things do I need to create the binary black hole merger rate from LIGO? Of course, with this, we can reproduce the rates. Every theorist can reproduce the rates because that's kind of what we do. Is there something, though, that we can get a handle on that is unique to formation in dense stellar environments, or some sort of parameter that can only come from one formation channel? And the answer to this turns out to be yes. I need to use these three-body encounters to create bound binaries in dense star clusters. To do this right, if I have a nearby encounter, I need some way to dissipate energy and angular momentum in order to create a bound binary from unbound particles. Now, I can do that with a third interloping particle in Newtonian physics, or I can do that with gravitational waves itself. Gravitational waves, right, subtract energy and angular momentum from a system. And so if I look at one of these just sort of encounters that you see in a dense star cluster between a binary and a single star, and this time, in this case, I'm integrating a binary single encounter in a Newtonian sense, but I've added relativistic corrections, including gravitational wave emission. And eventually what's going to happen is between these many, many close paracenter passages between the black holes, two of these black holes are going to wander so close together that they emit gravitational waves and merge, creating a new black hole with, critically, a distinct eccentricity. So this is that same encounter from before, and I'm highlighting the gravitational wave along the bottom, and you can actually see that unlike a nice circular chirp that you've probably seen from all the pictures, this actually has some complex structure in it, and it entirely comes from the eccentricity left in the gravitational wave. Put more simply, LIGO can actually measure the difference between circular mergers and eccentric mergers. And so we decided to just play the game. What do these things look like? What are the eccentricities you expect from binary stars versus dense star clusters? From binary stars, most of your eccentricities are going to be around 10 to the minus 7 when they hit the LIGO band. LIGO will never ever see that. But from clusters, you get this very broad distribution that goes all the way up to eccentricities of nearly 1. And if I compare where these different binary black holes are coming from, about 10% of them come from those captures, where you essentially have two black holes whiz by one another, emit a pulse of essentially Bremsstrahlung radiation, but in gravitational waves, and form a rapidly merging binary. And so the final part of this is, we want to compare this to the cosmological estimate. Can we combine this estimate with what we think we know about star cluster formation across cosmic time and create a unique observable? And so that takes me to this last point here, which is that combining this cosmological model that was done purely with halo merger trees and our best understanding of galaxy assembly with our understanding of collisional star cluster physics and gravitational wave physics, we can actually make predictions for how many of these mergers will be measurably eccentric in the LIGO-Virgo band. And it turns out that maybe about 1 merger per gigaparsec cube per year in the local universe will have an eccentricity that is measurable by LIGO. And so that's going to let us start to actually do astrophysics with these things, where we pull apart these populations and can actually do essentially detailed model comparison and population inference with what LIGO is providing. I always like to say that, basically gravitational waves right now is where exoplanets was circa 2011. There were a few detections, but Kepler hadn't really started putting out tons of light curves, and we're about to go to this regime where we're going to start getting hundreds of binary black hole mergers per year. And at that point, this is going to go from a few neat detections to full-on bona fide gravitational wave astronomy. And this is it. Thank you so much. Mm-hmm.
Then with one source it became a swarm, and then with more than one we had cosmology. So
Yeah. And very neatly, so I don't know if everybody saw the latest catalog paper that LIGO put out. They have their first detection at what I would call approaching cosmological distances. So now they have one binary black hole merger at redshift 0.5, which, okay, compared to what some people do, especially here, is not actually cosmology, but it's at least poking into that regime. And we can start to measure, potentially, the redshift evolution of the binary black hole merger rate, which really helps us link it up to our understanding of star formation and galaxy assembly.
Do the different models predict anything different in the mass functions?
Yes, but it's highly tunable. So you can get differences in the mass, but because you can essentially adjust your assumptions about common envelope efficiency or your initial binary parameters or your initial star cluster parameters, it turns out you can really adjust those knobs one way or the other to get whatever you want. The reason I like eccentricity, among other things, is that you really can't get that from a binary star. There's no real way to get out of a common envelope and not have dynamical friction circularize the orbit. Now the eccentricity measurement is similar between different formation channel or dynamical formation channels. So there's a lot of different things with a third or fourth companion that can produce eccentric mergers, but you can't really get that through anything that comes from a binary star.
Can you remind us with the current sample what are the constraints?
Well, so that's the part I kind of skipped over because LIGO is not actually looking at this very carefully right now because it's an insanely hard problem. It turns out writing down really good relativistic waveforms to do template comparison with eccentric waveforms is actually very difficult. So right now, the constraints that I've seen all say everything that LIGO has seen is below 0.1, but they were a little cheeky in that constraint because the reason they said that is if it was greater than 0.1, they would not have gotten a good enough fit to pre-existing models. So it's not so much that everything they've seen has an eccentricity of below 0.1, it's that they wouldn't have actually seen anything with an eccentricity greater than 0.1. There are people that have been doing more work on these templates and are going back through the data with a sort of higher fidelity search right now. So, not all is lost. People aren't ignoring this. It's just a hard problem that requires some significant finesse.
So the peak, if you go to higher redshift, is due to the cosmic star formation rate.
Mm-hmm.
Some lag factor. Do you win, or can you the same information if you look just in the current universe, but split the galaxies according to the star formation rates?
So you can, and people have done this for. People have done this trying to essentially establish like where did the first couple or the heavy black holes come from, because we think those had to come from low metallicity environments. And so if you assume that your heavy black holes were formed from, say, binary stars and through a common envelope channel, then the assumption is that those probably had to come from some sort of low metallicity active star forming galaxy in the local universe. There's a paper by Astrid Lamberts where she looks at this. It's a little bit harder to do for dense star clusters because the delay times there can be many gigayears. So it's possible they formed these binaries at redshift 2, and then they just hung out in the galactic field for 10 gigayears. The other problem is, of course, LIGO's sky localization for black holes is not the best. And that's mostly just because they're at higher redshifts and have higher sky, or larger error bars on the sky. Mm-hmm. Yeah. Although there you have the problem that you have to get something with a relatively close mass ratio, because if you merge a neutron star with a 30 solar mass black hole, you're not getting a tidal disruption. It'll essentially swallow it whole. I should point out just one more thing to keep this exciting. Right now, LIGO will probably only see up to maybe Zia 1, but there are proposed third generation detectors, things like Einstein Telescope, Cosmic Explorer, that are sort of the follow-ups to LIGO, and some of their design specs have them seeing binary black hole mergers beyond redshift 10. Exactly. And unless primordial black holes are out there being weird, there's not exactly a lot of evidence that there should be black holes before redshift 10. So it's entirely conceivable that within the next 20 years, we'll observe every binary black hole merger within the universe, which is an awesome thing to be able to say. Yo.
How the distributions will change as a function of redshift. You were talking about how the rate will change as a function of redshift, but how will the eccentricity mass ratio change?
I've looked at some of that, but no, I haven't really published that.
Yeah.
Because I think really what we need to start doing is I can't just keep publishing distribution. I mean, I can, but
yeah, right.
Yeah. This is part of the problem. I need a way to generate bigger populations in order to do this really well, which is what all of my faculty applications are filled with.
And there could be some quicker ways, estimates too.
I think so, yeah. Speaking of, are you... Oh, right, good point. Just talk about all of my future plans to an entire audience of people. Speaking of future... what the fuck am I saying?